Section for Chapter 3 is Section 5. And it's going to be a relatively short section because we've already done some of the applications and modeling. What I want to do is I want to do one more word problem, okay, one more application. And this is dealing with population growth. So really quickly, the formula that we're going to be using for this problem we're going to do, it's going to look like this. And it should strike a resemblance because back in 3.1, we did a compound interest formula. And it looked, as you can see, it looks nearly identical, right? Now, the only difference is what we're going to do and what we label is this can now be carried forward to anything dealing with exponential growth or exponential decay. For example, population growth, population decay. Well, let's make sure we understand each part. So the A, let's start with it's equal to A, meaning it's equal to some amount, right? Now that amount might be, it's equal to the population on a certain year. So that is what A stands for. Now, this other piece is A with a subscript of 0. And that's going to be the starting amount. So you could think about that as the starting population, if you'd like. The K, instead of referring to it as interest rate, we're going to refer to it as growth rate. Because you can think about even if you were looking at fruit flies in a laboratory, they would have a certain growth rate. T is the same; it's just going to remain time in years. So what is it that determines whether it's going to be population growth or decay, right? Population growth, population decay. But what is it that determines? What is it in here that determines whether you're dealing with growth or decay? Well, the variable that determines growth or decay is this. Now, for those of you that like money analogies, you could think of it as the interest rate is what determines if you're dealing with growth. Of course, that falls apart slightly, right? Because we don't normally think about negative interest rates. That being said, what we're going to do is I'm going to go ahead and write that down for you. So if you have a value of K that's greater than 0, then what you have is exponential growth. If you have a model of K that is less than 0, right, you're going to be dealing with negative growth rate, meaning decay. Okay, a couple pieces of trivia. So what you're looking at is I've just done a little plot of world population over time. And now, if I were to look up population in 2020, I'm assuming world population somewhere around 7.5, 7.8, 7.6 billion, right? So let's just go 7.5 billion people, right? Now remember, there's a billion has 1,000 million. Just to make sure you understand, if you have $1 billion, you have 1,000 million dollars. Well, if we start winding back the clock, so you got 2020. You have, let's just go with 7.5 billion. Now, if you go back to 1999, world population at 6 billion. 74, 4 billion. 1930, 2 billion. And our first billion, the first, the year that the world population hit its first billion was about 1804. Now that's interesting if you think about that. It took us till 1804 to reach our first 1 billion people on Earth. It took us till 1974 to reach our first 4 billion. And just look at the growth, right? We're already at almost 8 billion in 2020. It's interesting. Now you might think, wow, this, if I were to ask you what's the population growth rate, world population growth rate, you might think that, man, we must be growing 5% per year, 8% per year, 10%. It's actually, all of this was done with about 1.1% growth per year. Does that make sense to you? Like if I told you I was going to pay, your bank was going to pay you 1.1% interest rate, you wouldn't, I mean, I don't know, I doubt you would jump out of your seat in excitement over that interest rate. And 1.1% population growth doesn't seem like much, but that interest rate, just that small percentage growth can lead to a massive population over time. So what's the question? Well, we're going to look at, instead of looking at world population, we're going to look at U.S. population. And we're going to be grabbing some information from this chart, except I believe that everything you need is nestled into this question, so we don't really need to look at the chart. But let me read. So the graph in figure 3.22 shows the U.S. population, and now we're in millions, not billions, for 5 selected years from 1970 through 2010. All right. So we got 5 years of, so in 2010, we were, about 308 million population in the United States. 1970, we were at 203.3 million. Okay. So they go through and they give us some information. In 1970, the population is 203.3 million. By 2010, it was 308.7 million. Now comes the part where we find out what they want us to do. We want to find an exponential growth function. That's this. That models the data for 1970 through 2010. All right. So I think we kind of understand what it is they want from us. All I'm going to do right now is just take some quick notes. So we got 1970 with a population of 203.3 million. And 2010, we had a population of 308.7. Right, so this is in millions. All right. So let's also make sure let's figure out what is it that we have and what is it that we will be solving for. Let's start with the amounts. So the starting population would be the population of 1970. But do you see how in this case we actually know the end population, well, for this model, which was 2010. So let me start to capture that. So in this problem, A sub 0 is 203.3. A, which is the amount over time is 308.7. Okay, now, what else would we need? Well, remember, the E is not a variable, right? That's our base. The question is, do we have K or do we have T? Well, T is time in years, and we know how many years have passed by from 1970 to 2010, right? So in this case, T would be equal to 40. What we don't have in this problem is K. We don't know the growth rate of the US population over that period. But let's start to plug in the information we have. So we got 308.7 is equal to 203.3. E to the power of, now T is 40, so it's K times 40, or just 40K. Okay, piece of advice, if you can make life a lot easier on yourself, if you just leave this as 308.7 and leave this as 203.3, and then whatever your answer is, we know that that's in millions. Because I've seen a lot of students write this out as, 308 million, like they write the whole 1 million out. And then they start running out of space on their calculator. Their screen just can't support that many characters. So just leave it as 308.7, leave it as 203.3, but just understand that you know that you're talking millions. Ready? All right, so it says find an exponential growth function that models 1970 through 2010. We almost have that, except we're missing the K, right? So that's what we're going to do right now. We're going to solve for K. But wait a minute, we've been down this road before. So just like last section, we'll go ahead and we want to isolate this e to the 40k. Well, we can do that if we just divide both sides by 203.3. So that leaves me with 308.7 over 203.3. And what is that equal to? That's equal to e to the power of 40k. All right, well, if you want to solve for k, you're going to need, since k is, the variable is in an exponent, remember, we're going to end up taking ln of both sides. And when you take ln of both sides, that allows us to bring that 40k up front, and we can solve for k. So let me go ahead and do that now. So we're going to take ln of both sides. I'm going to go ahead and write that. So that's ln of 308.7 over 203.3. That's going to be equal to, let's go ahead and bring that 40k out front. 40k ln of e. Do you remember what I said about ln of e? Right? Ln of e is equal to 1. So that just turns into 1. Okay, so we're almost there. What is k? K is equal to, well, just divide this side by 40, divide this side by 40, and there you go. So k is equal to ln of 308.7 over 203.3 divided by 40. Now, since we're dealing with word problems, and we're dealing with population, this is one of these types of problems where it's okay to go ahead and start introducing some error. Right? So we can grab our calculator and round that, and that ends up being K is approximately 0.01. Right, it's 1%. So the U.S. has had about 1% population growth since 1970. So what's left? Well, as soon as we take this 0.01 and go back and plug it in for K, there you go. You're all done. You have your formula. I'm going to do that on the next page. So the final result for A is going to be A is equal to 203.3 E to the power of 0.01 T. So, and at this point, you should be able to come along and plug in a time from 1970 to 2010. And what should come back out should be the population. So if you plug in 0, that would mean you're looking at the population in, was it 1970? Yeah, in 1970. If you plugged in, 10, you'd be looking at the population in 1980, and so forth. Let's go back to the previous page and read part B. Interesting. So now that we have a model, population model, can we use that to figure out what year the United States will have 335 million? So, what year will the population A equal 335 million? So do you understand that really what all we're going to do now that we have our model, we can just take 335, plug it in here for A, and do exactly what we've been doing all along, now just solve for T. And that'll tell the time, the year, when the population would be expected to be 335 million. So let's just go ahead and finish that up. So let me write it in. So I got 335 is equal to 203.3 e to the power of 0.01 t. And you guessed it, we're going to solve for t using the exact same steps from part A. So divide by 203.3, divide by 203.3. And that leaves me with e to the power of 0.01 t. You remember what we do from here? I hope so. So it's just, you want to solve for t, right? So let's use that ln of both sides. And let's write that. So now it's going to be ln 335 over 203.3 is equal to, remember, we can now bring that exponent, bring all of that out front. So 0.01 t ln of e. And that, again, that ln of e cancels because it just equals 1. Almost done. All we got to do now is just solve for t. So ln 335 over 203.3 divided by 0.01. Well, let's see what you get. So I'm getting a time of roughly 50. But they didn't ask you what is t. They asked what year. So this is important. What year? So we have the right answer. But wait a minute. What we want to go from 1970, right? That's year 0, or t is 0. If we add 50, then we'll be at the year what? 2020. Right, so that would be 50. So when would we expect the population to be 335 million in the US? Well, we would, based on this model, we would expect that to have occurred in the year 2020 this year. Is that correct? I don't know. You'll have to go in and check on your own. See if the population's 335 million in the US today. That will conclude our last bit of theory from chapter 3.